Okay, in this video, we're going to be looking at the derivatives of trigonometric functions. So make sure you have your notes packet out and you're following along with this. Okay, so it says at the top, using the derivatives of sine and cosine, you can find the derivatives of the other four trig functions as well. Let's start by finding the derivative of the sine function using the limit definition of a derivative. All right, so we're going to spend a good bit of this first page essentially just proving, finding, but also proving where the derivative of sine of x comes from, so that you can kind of trust that these shortcut derivatives we're going to learn at the bottom of the page don't just kind of fall out of the sky, that they have their roots in algebra and you can derive them if you need to. We are not going to ask you to derive these by hand on a quiz or a test, but let's check out the algebra that is behind it. So example 1 says, find f prime of x if f of x equals sine of x using the limit definition of a derivative. All right, so we're going to kind of break this down into bite-sized chunks, and I'm going to try to go through it as efficiently as I can, since this is not something I'm going to ask you to do on a quiz or test. Okay, so first off, we need to remember that the limit as x approaches 0 of sine of x over x is 1. All right, check. All right, then we're going to take something we're going to need later, and we're going to kind of break down this limit and evaluate this one in, what's it called, part B, before we actually do the limit derivative. Okay, so it says investigate the following limit. The limit as x approaches 0 of the cosine of x minus 1 over x. It says, what do you think the value of this limit is? You can go into your calculator and see what you think it is, but let's look at it algebraically. Okay, so let's set it up first. So we've got the limit as x approaches 0 of cosine of x minus 1 over x. The skill we're going to use to start this one out is to use our difference of squares, and we're going to multiply by cosine of x plus 1 over cosine of x plus 1 in order to get that numerator to be a difference of squares. So we're multiplying by the conjugate of that numerator, and then what happens on the top is we get that difference of squares. So first term squared is cosine squared, second term squared is 1, and then we subtract them. Okay, in the denominator, let's keep it factored out. Don't distribute that x through quite yet. And then what we can do is we can say, hey, I remember that this cosine squared of x minus 1, that's two terms of our Pythagorean identity. And so if we refer to our Pythagorean identity and we solve it for cosine squared of x minus 1, then we get that it's equivalent to negative sine squared of x. So we can substitute that negative sine squared of x in place of that cosine squared of x minus 1. And then we're going to manipulate this a little bit, seeing that this is really close to having that sine of x over x limit that we know is equal to 1 as x approaches 0. Then we're going to split that sine squared of x into two sine factors, and we're going to group that x along with one of them, and then we're going to split that limit up so that we've got the limit as x approaches 0 of sine of x over x that we know is 1 as one factor, and then the rest as our other factor. Okay, and then we can try direct substitution with what is left, and we're going to get 0 over 2 with what is left. And we know that first factor is a 1, so 1 times 0 does give us 0. All right, so again, haven't even calculated a derivative yet, but we've got this piece, the fact that the limit as x approaches 0 of cosine of x minus 1 over x is 0. We're going to need that in just a few minutes. Okay, so part C, next part. Now it says find the derivative of sine of x using the limit definition of the derivative. Okay, so let's go back to our limit-based definition of our derivative. We're going to use our standard one. Again, we're trying to find the derivative of sine of x. So if we substitute in sine into our function, then we're going to get the limit as h approaches 0 of sine of x plus h minus sine of x over h. And then this sine of x plus h, algebraically, there's not a whole lot to do with it. We can't just split that into sine of x plus sine of h. That's not how trig works. But we do have an identity for the sum of angles in a sine and in a cosine function, if you remember back to pre-calc. And so if we call on that identity, then it said if you take the sine of the first angle times the cosine of the second angle plus the cosine of the first angle times the sine of the second angle, then that's equivalent to sine of x plus h. Okay, so if we substitute all that in, we still have the minus sine of x from the minus f of x part in the numerator. All of that is over h. And because we've got this, let's see if I can change highlighters, this sine of x term here, or factor in that first term here, and we have a minus sine of x at the end, if we group those together, and then the leftover plus cosine of x sine of h term comes second, then we can do our Hart method split, and we got essentially a binomial on top over a monomial. So we can split this up into two separate fractions. And essentially we're just going to kind of drill this down into smaller and smaller bite-sized pieces that's more manageable for this limit. Okay, because right now we're still going to get indeterminate form if we try direct substitution. So let's see, what are we doing next? We're going to factor out this sine of x in both of these terms here. So factoring out that sine of x. So the leftovers are cosine of h minus 1, and we're still over h. And then the second part is this second part here. Okay, so now that we've got two separate limits, and we've got a product in the top and the h in the bottom, so now we're going to split this up again. We're going to go through and we're going to say, well, here's our only x term, so we're going to give that limit, or that factor its own limit. So limit as h approaches 0 sine of x. And then we're going to give this factor its own limit. Remember, we're not doing a derivative, so we don't have to do the product rule of a derivative. We're still, even though the bigger picture is we're evaluating derivative of sine of x, the process we're using is a limit. So one of our limit properties was we can split up factors and find the limit of each of those separate factors there. Okay, so finding the limit of that second piece, and then moving on to our whole big second term here. If we split that up the same way, take our cosine, give it its own limit, and then the sine of h over h is going to be a whole nother factor and a whole nother iteration of that sine of x over x limit that we know a value for. Now we can go piece by piece. So we can say, all right, so the limit as h approaches 0 of the sine of x. Well, there's no h in there, so that's going to stay sine of x. All right, the second piece here, the limit as h approaches 0 of cosine of h minus 1 over h. Well, that's what we spent all of part B finding, and we found that that comes to 0. So instead of doing all that within this problem, that's why we did part B separately. So now let's take that 0 and let's plug it into this problem. All right, and then the limit as h approaches 0 of the cosine of x. Again, there's no h in that cosine, so we're going to keep that cosine of x. And then here's this limit as x approaches 0 of sine of x over x, essentially. We know that is 1, and so there's that 1 factor there. So simplifying all that, anything times 0 is 0. Anything times 1 is itself. So we're left with 0 plus cosine of x, which is just cosine of x, which again, what we started off doing here was finding the derivative of sine of x. So we just found, essentially proved, that the derivative of sine of x is cosine of x using the limit-based definition. Now, thankfully, we don't have to do that every time. We've got this box of shortcuts that we're going to use from now on. Before we get to that box, this statement above says you can prove ddx of cosine of x equals the opposite of sine of x using the same method and the same two limits above. We're not going to do that right now, but you may be asked to do that in one of your homeworks tonight or tomorrow night. But here's our box of our 6 shortcuts for our 6 basic trig functions. You need to know these. So you need to have these committed to memory, make flashcards, star this section, make sure you come back and know these going forward. All right, add these to our list of math facts that you need to know. Okay, notice we've got our sine and cosine there that we just talked about. They include, tangent of x. So derivative of tangent of x is secant squared of x. And then our secondary trig functions. So the derivative of cotangent of x is the opposite of cosecant squared of x. The derivative of secant of x is secant of x tangent of x. And the derivative of cosecant of x is the opposite of cosecant of x cotangent of x. I want to challenge you to try to go beyond just memorizing these, but look for patterns, look for ways to connections and ways to remember these where you're not just kind of just force feeding memorization into your brains. All right, on the next page, we're going to do a couple of ways to prove where some of those other derivatives come from, and then we're going to start to apply them as we're more typically going to do going forward. Okay, so at the top, using the derivatives of sine of x and cosine of x, previous derivative rules we learned, and some algebraic massaging will enable us to prove the value of the other 4 derivatives. Okay, example 2 says, prove the derivative of the tangent of x is secant squared of x. All right, let's go through this one step at a time. So we're looking for a derivative of tangent of x. So again, going forward, what we can do, if this was just a part of another problem, is we can use our shortcut and go straight to secant squared of x. But this is showing that, hey, knowing the derivatives of sine and cosine, let's use those to our advantage and our other trig identities and algebra to show that it works in multiple ways. So derivative of tangent of x, rewrite tangent of x as sine over cosine. Now we have a quotient. Now we can use our quotient rule for derivatives, and we can say low d high minus high d low over low squared, and simplify. Okay, we've got cosine squared. We've got a double negative, so that's a plus. We've got sine squared. Cosine squared plus sine squared is our trig identity, so we can rewrite that as just 1. 1 over cosine squared is secant squared of x. And we're good to go. Okay, the green up there is just another more complicated route you could have taken. Okay, if you wanted to prove cotangent of x, it can be done in a similar way. I believe you'll asked to do that in your homework either tonight or tomorrow night. Okay, example 3, derivative of secant of x. Let's do this in a similar way. Again, this is a proof. Going forward, you can use a shortcut. This is showing that it works. Secant of x is the same thing as 1 over cosine of x. Using that reciprocal rule, we've created a quotient with a cosine. We know the derivative of cosine is the opposite of sine. So now let's use that quotient rule for a derivative. So low d high minus high d low all over low squared. Simplify, that first term is going to be 0. Minus a negative is a positive. We got a sign in there. And cosine squared of x is still in the denominator. So we don't have a rule for that, but we can split that cosine up and slide the sine over and group them. So we've got sine over cosine is tangent. 1 over cosine is secant. It doesn't matter which order you use, tangent, secant, or secant, tangent. But that is our derivative for secant of x. Okay, likewise, cosecant of x can be done. Again, I think you'll be asked to do that in your homework or some practice coming up this week. All right, example 4. Let's actually use these in problems. So 4 says find the derivative of each of the following functions, and we're given a handful of these. Let's do the first 2 together, and then I'm going to ask you guys to do the rest on your own. And check your work with the completed notes and the OneNote or on Canvas. Okay, so first up, we got f of x equals x squared times sine of x. I want you to see that that's a product, and that x squared is u, and sine of x is v. And so we're going to need to use the product rule. Okay, so I might just go ahead and come down here and say du is 2x, dv, derivative of sine we just learned is cosine of x. So now we can just plug and play if we remember our product rule. So product rule says first d last, or u, that's going to look like a fraction, u dv plus v du. Okay, substituting those in, we get x squared cosine of x plus 2x sine of x. And there's no like terms there. There's nothing else we can do, so we're going to leave it just like that. Okay, part B, we've got a quotient. We've got cosine of x over x. We want to find this derivative. It's already quotient, so let's use our quotient rule. So low d high minus high d low, all over low squared. Again, we're just kind of folding in our new shortcuts for derivatives of trig functions into the rest of the rules that we already know. All right, simplify what you can. Not a whole lot there. Leave it like this. Don't make it any more complicated than it needs to be. Okay, C, D, and E. You guys try yourselves. Use those rules that you already know in addition to the new trig rules. Okay, on this last page here, the gist of this last page is that your TI calculator can actually graph a derivative. It's honestly not super useful, and it's not a required skill like just doing inderive itself is. But it's nice to know that your calculator can give you a visual for the derivative of a function. So since we got TI-84s in our classroom, I'm going to skip just to this part here. I don't have a TI with me, but if you go into your y equals and go into y1, then you can go ahead and use the inderived function within y1 and type it in the same way you would as if you were evaluating the derivative at a point. The main difference is that instead of telling it to evaluate at an actual constant, then it's just going to spit out a number value. You're going to get a horizontal line graph. You're going to just plug in x again on the other side of that x equals equation. And so it's going to just kind of continuously be plugging in those values, and it's going to plug in the derivative at each point. You're going to be able to trace that derivative curve. Okay, so try that in your TI calculator or borrow one from the card up front. And then I want you to try example 5 and 6. Sketch what those derivatives look like and answer the questions below. And then I'll take questions on this when I'm back in class next. And our next topic is going to be on the chain rule, which is going to give us the opportunity to take derivatives of composite functions. Hope that helps. Y'all have a good one.